Hello guys, how's it going? now we're gonna now we're gonna go now we're gonna go to the introduction to the embeddings with OpenAI API, which is the sixth course, and a associate AI engineer for developers. So it's a career track, and we're already in the sixth course. This is probably having a bit more, but yeah, let's continue here. Now I think we need to create a new directory for this, so it's gonna be unless I have this one as there, embed links open AI. So let's go there, and now that we are doing this, let's close all of this. Now we have our give me 1 second, some client call me. Okay guys, it's because someone just called for one of my businesses. So anyway, give me 1 second. I'm just gonna send an SMS. Okay, so I just sent a link for one of my. I think at some point after this course, I'm gonna make an agent to just receive phone calls and just reply to the messages because a lot of the questions are really repetitive. Anyway, we're here. We're on the screen, and now we're gonna start with embedding, guys. So let's just. I saw in my last live that this desktop audio is not really strong, so I'm gonna put it a bit more probably, and then let's start.
Hi, welcome to the course. I'm Emmanuel, and I will be your guide as we learn about embeddings and the powerful applications they unlock. Let's dive right in. Embeddings are a fundamental concept in natural language processing, or NLP, where text, which can be words, phrases, or entire documents, are represented in numerical form. More specifically, embeddings model map text onto a multi-dimensional space, or vector space, and the numbers outputted by the model represent the location of the text in that space. More similar pieces of text or words, like teacher and student, are mapped closer together in the space and dissimilar words are mapped further away. This ability to map similar and dissimilar words means that embeddings models can be used to capture the semantic meaning of text. By semantic meaning, we mean that the full context and intent of the word is captured. For example, which way is it to the supermarket? And could I have directions to the shop? Are semantically very similar, but only share two words in common. A model using embeddings would recognize the semantic similarity between the two variations and return similar information. Let's take a look at some of the most powerful use cases being enabled by embedding models. Embeddings enable the creation of semantic search engines. Traditional search engines use keyword pattern recognition to return relevant results. For example, searching comfortable running shoes on a traditional search engine may return results containing the keywords comfortable, running, and shoes, but may miss the true intent behind the searcher's query. It will also miss variations on the word provided, like soft instead of comfortable and sneakers instead of shoes. Semantic search engines use embeddings to better understand the intent and context behind search queries to return more relevant results. The search query would be passed to an embedding model to generate the numbers that map it onto the vector space, and the embedded results closest to it would be returned. Embeddings also enable more sophisticated recommendation systems. For example, a job posting website could use embedding models to recommend jobs for its users based on the description of jobs they have already viewed. Using a semantic recommendation system means that even if job titles vary, the system will recommend jobs with descriptions that are most semantically similar to the jobs that have been previously viewed. The final use case we'll discuss is classification, which works very similarly to recommendation. This can be used to classify sentiment, cluster observations, or perform categorization, all based on the semantic similarity between text. We could use embeddings to classify news headlines by embedding the headline and assigning the label closest to it. OpenAI provides access to their embedding models via the embeddings endpoint, and requests to it take a very similar form to other OpenAI endpoints. We'll use the OpenAI library to create requests to the OpenAI API, which also requires us to have an OpenAI API key. To begin our request, we first need to instantiate the OpenAI client and pass it our API key. To create the request, we call the create method on client.embeddings. An OpenAI embeddings model can be specified with the model argument, and the text to embed is passed to the input argument. We are specifying the input here as a text string, but the argument also accepts a list of strings. Finally, we'll call the model dump method on the response to convert it into a dictionary, which is easier to work with and print the result. The response from the API is extremely long, as the embedding models outputs 1,536 numbers to represent the input string. Because we converted response from the dictionary, which is easier.
So you put the, instead of, you call the embeddings that create, you put the model and then you put the input, which is the text, and then
work
you
with and print the result.
Transform.
The response from the API is extremely long.
It's an object, which is a list, and then the data, and the embedding is a list.
As the embedding models outputs 1,536 numbers to represent the input string. Because we converted the response into a dictionary, we can dig into it using lists and dictionary subsetting. Here we can print the full list of 1,536 numbers representing our text. We'll discuss these numbers in more detail next, but for now, let's practice.
All right. So, which of the following statements about embedding models are correct? They create numerical representations of text? Yes. They output the text most similar to the input? Not necessarily. It can be really different, but mathematically they could have the similar meaning. To capture the semantic meaning behind the text, yes. Or in a piece of text, I am not sure. So this is okay. The embeddings applications. Embedding models convert text into numerical representations that are able to capture the context and intent behind the text. This unlocks powerful applications beyond what is possible with other types of AI models. In this exercise, you will test your ability to identify use cases for embedding models. So, customer reviews. So this transforms into numerical numbers, okay? Search engines also here in embeddings. House price prediction. I think this is not embeddings. This is just like probably some other ML technique. Categorizing products. This is also in embeddings. Book recommendation system. Probably also yes. Real-time stock trading. This is not embeddings. This is also some any other ML technique. That's good. In this exercise, you create your very first embeddings using the OpenAI API. So here I will do OpenAI, and this will be client.embeddings.create, and then I do this, and then inside of here I pass the model, which will be this one here. Then I will pass the input, which text, is it text input? Yeah, let's create this. No, sorry, just input then. Input, it's equal to the okay, text that you wish. Okay, so why does the cow, or why when the sparrow was selected as the best culinary destination in the world? And then in the response I should get response, and it was response something like dumps, and then I'll get the response dictionary. What even? Okay, it's also the same problem that we had before. Maybe we need to just reload the page. All right, so let's do this. And let's run this. Has not attribute dumps. So in here, model dump. Okay, then it should be good. Yeah, and it's showing you the embedding. Okay, so first of all, it worked, and now we need to just, I need more space here. Okay, and then in here we have the embeddings OpenAI. As we did here, we also need to do the OpenAI client. Yeah, so we need to put here in embeddings too, and then here we're gonna make a new file, which is gonna be touch1 embeddings example, py. Then we already have it here in embeddings. Then here we can copy this code, but because we have already defined the client, I will just do from OpenAI client import client. So it's the same client, but in this case we will use the embeddings, not the completions. Because as you remember in the other where was this? And here we were doing the chat completions create. Now to create the embeddings we need to do this. Okay, so now let's run this, and we need to see the log of the embeddings, which is the dictionary. Let's wait for a few seconds to Yeah, it's really big. Whoa, it's huge. Okay, worked. Let's submit this. Perfect. Let's continue. You have been able to successfully use the OpenAI embedding endpoint to embed text data. And in this exercise, you will finish this off by extracting information from the API response. Okay. You have provided with the response from the embeddings API, which has already been converted into dictionary and stored into response dict. All right. And you will need to extract the desired information from this. You can view this content structure. Extract and print. So I should print the response dict. And I guess in this sample, I should get the, okay, it should be the usage. And then in the usage, I should get the total tokens. So I should get total tokens. All right. 6. Okay, that's one. And the second one is, and now so this should be the response dict, and then in here I should get the total tokens. No, embeddings, right? So in this case, I'm going to do the data, then the first element of the array, and then I need to get the embedding. And this is the array. Awesome. So now let's do this copy. Not here, here. And there's gonna be 2 embeddings response. In that case, we do the same, but in this case, we're gonna print the and in the first exercise is gonna be this total amount of tokens, and we're just gonna put it there directly in the second one, all of the embeddings. So if we run this one, which is gonna be 2, we're gonna get the total tokens using in the embeddings and the embedding by its own. Here's the embedding, and let's go a bit more up. Yeah, here, and here's the number of tokens, 16. It's perfect. Let's jump into the next one. Now investigating the vector space.
Welcome back. In this video, we'll discuss embedding multiple inputs and how to store, handle, and explore these embeddings. Let's dive in. We'll be working with a dataset of news articles stored in a list of dictionaries. Each article has a headline stored under the headline key and a topic stored under the topic key. We'll embed each headline's text and add them back into the headlines dictionary stored under the embedding key. To start, we'll extract each headline stored under the topic key, the head of dictionaries. Working with a dataset of news articles stored in a list of dictionaries.
Okay,
Each article has a headline stored under the headline key and a topic stored under the topic key. We'll embed each headline's text and add them back into the headlines dictionary stored under the embedding key. To start, we'll extract each article's headline using a list comprehension, accessing the headline key from each dictionary. To compute the embeddings, we can pass this entire list as an input to the create method. Patching the embeddings in this way is much more efficient than making API calls for each input. The response output only differs from the single input case in one way. Where before the list under the data key contained a single dictionary for the embeddings, in the multiple input case, there is one dictionary for each input. To extract these embeddings from the response and store them in the articles list of dictionaries, we loop over the indexes and articles using enumerate. For each article, we assign the embedding at the same index in the response to the article's embedding key. Let's print the first two articles. Voila! We've successfully created embeddings for multiple inputs. Let's investigate these numbers more closely. For the first article in the list, the embeddings model returned 1,536 numbers representing the semantic meaning of its headline, or in other words, its position or vector in the vector space. Let's take a look at another, longer headline. We get 1,536 numbers again. This is a key property of OpenAI's embedding models. They always return 1,536 numbers, no matter the input. Let's visualize our embeddings to better understand the model's results. We'll first need to reduce the number of dimensions.
Okay, so as far as I understand, we always generate the same amount of number of embeddings. So the length of the array is always the same.
Let's visualize our embeddings to better understand the model's results. We'll first need to reduce the number of dimensions from 1,536 to something more manageable, like 2. There are a lot of techniques for performing dimensionality reduction, but we'll be using tsne, or T-distributed stochastic neighbor embedding. Although we won't be going into the mechanics of how tsne works, you can check out the datacamp link to learn more. We'll implement tsne using scikit-learn, a popular Python package for machine learning tasks. First, we import tsne from sklearn.manifold and numpy as np. Next, we'll extract the embeddings from our articles list of dictionaries using list comprehension. To implement tsne, we create a tsne instance and assign it to the tsne variable. We've specified two arguments: n components, the number of dimensions we want to reduce to, 2, and perplexity, which is used by the algorithm in the transformation. The default value of 30 is normally fine, but for smaller datasets, it must be reduced to a number less than the number of data points. We have 10 articles in our dataset, so we've reduced perplexity to 5. Finally, to perform the tsne transformation, we call the fit transform method on the tsne object, passing it the embeddings as a numpy array.
Tsne fit transform. NP array embeddings 2D. So with the TSNE, you reduce the dimensionality, you pass how many dimensions you want to get at the end, and the perplexity I don't understand really quite well, but it's probably another parameter you need to put there. Which number should I put there? I still don't understand, but let's see. Embeddings in 2D. Gonna fit transform NP array embeddings. So it's gonna convert so it's gonna convert an array on arrays into an NumPy array, because that's probably what the fit transform receives.
This will return the transformed embeddings in a NumPy array with n component dimensions, which we can now visualize. Although tsne is useful for exploring and visualizing higher dimensions, it will result in the loss of some information in the transformation, so it should be used with caution. To visualize these transformed embeddings, we call plt.scatter from matplotlib on the first and second columns of the embeddings to the array. We'll also include some code.
What?
plt.scatter from matplotlib on the first and second columns of the embeddings to the array.
So I'm gonna print and the first and second column of the. So now I have the 2D array, and I'm gonna have.
We'll also include some code to extract the article topics, annotate the plot with them, and display the plot. Here is the plot. Notice that headlines with the same topic were clustered more closely together. In other words, the model captured the semantic meaning of the headlines and mapped them based on it.
Okay, then we just transform multidimensional just two-dimensional.
The model captured the semantic meaning of the headlines and mapped them based on it. In the next video, we'll discuss how to compute the similarity between embeddings to enable applications like semantic search.
Okay, so the thing here is like, so here what I'm getting is getting all of the elements of the, what is it? All of the first column of all of the rows. So it's getting an array of.
From matplotlib embeddings used with caution. To visualize these transformed embeddings, we call plt.scatter from matplotlib on the first and second columns of the embeddings 2D array. We'll also include some code to extract the article topics, annotate the plot.
Okay, what I understand is like here's, I think it's generating two arrays, which is like x and y dimension. And PLT, so for each one of them, because here's already generating the two-dimension like plot, but it's trying to put now the enumerate topics, and it's putting the topic into the position. For example, this will be the why. So here is trying to do what? Like it's trying to put in the same point as we did here. Because I think here's generating the values in x, and here's generating the values on y. Then I'm getting the value on x and y, and in the same point I'm putting the topic. Okay, so I got what I mean, but I only need to code it. I'm just explaining
display
more.
the plot. Here is the plot. Notice that headlines with the same topic were clustered more closely together. In other words, the model captured the semantic meaning of the headlines and mapped them based on it. In the next video, we'll discuss how to compute the similarity between embeddings to enable applications like semantic search. Time to practice.
Okay. Okay, guys. I think I'm gonna stop here. I'm gonna take a walk with my dog, take a small shower, and then continue with this. Okay.